Okay, Assalamualaikum and good morning, everyone. So today is going to be our, I suppose, the last lecture uh, for this semester, but there will be other recorded lectures that I shall upload later on. Okay, so let me go through the topic that we are supposed to cover today. Essentially, I hope you can see the screen. Somebody? Everyone can hear me, or am I speaking loud? No. Okay, great. Right. Okay. So today we're going to look at line integrals. Okay. So recall yesterday what we had was to look at the gradient operator. So that gives you the idea of a differentiation in terms of vectors. So today, as you know, part of calculus will be integration. So that's the essential topic for today. Okay. So we have seen previously the idea of work done, for example, is given by, say, a force taking the scalar product with a particular uh, displacement over here. So instead of having a displacement in a sort of a constant sense, like no, you just have f dot ds. Sorry, f dot s, where normally one thinks of this f is sort of having a constant what you call numerical value. So there is not. I mean, it's a very special case. So usually, what one would have is essentially your force will depend on your coordinates, and you would like to see how the work done by this force along some particular curve. So this is an example in this picture over here. Uh, a body or no, a particle, for example, is going to be what we call move from the point A to B under the influence of this particular force. Essentially varies from no, over each point of this curve. No, it varies according to this what I call function, for example. Okay, so we would like to do how to do this particular integral. So one of the things that one should remember that it's just a kind of a generalization of your one-dimensional integral. But here, instead of having one particular variable, so these are usually our specified variable, single variable. Now one is no generalizing this in a way that one could actually have different variables coming in. So this is what we're going to look at. So you have your f as a function of x, y, z, and then your curve over here is going to be an element of the curve will be given by this dr written in terms of your infinitesimal elements of dx, dy, dz. So whenever you take the dot product, you will get something of much more general nature, where it involves both x, sorry, well, it's not both, there are three different variables, so there are no, having dx, dy, dz all together in one particular integral. But the fact is it's still one dimensional because you are looking at a particular curve. Okay, the only difference with the one before, now this curve may not necessarily be given in a single variable. Okay. So, okay, let's look at an example where we can actually do this. So here's an example which the force is given by this expression over here. So this is in two dimensions because there's only a unit vector I and j. Okay, and then your path is going to be determined by this the position vector, really, and how it's going to be determined what path it is. It's going to be usually given in the question or specified by some means. Okay, so here what one does is to integrate. So if you just take the dot product between your f, okay, with your dr, you're going to get this expression over here. So your integral over here would have to be of this nature, and you can see now this is no, it's not like your normal integration where you only integrate over a single variable. Here you are integrating over two variables, x and y, and your integrand or your function that's going to be integrated also involve x and y. Okay, like here. Okay, so now how does this work? Well, you need to specify the path over which you need to do the integral. So here there must be a determined path, okay, because it's not specified there. So the path has to be determined. And in this particular example, there is given four different paths. Okay, first one is the straight line between 0, 0 to 2, 1. Well, all of them are going from 0 to 0, 0 to 2, 1. Okay, so in other words, over here the path is from 0, 0 to 1. Okay, so in other words, the endpoints of the line integral are actually given. Okay, and the only thing that was not specified is which path are you going to take. So here path 1 is the straight line, and I think the equation is given here, y equals half x. Okay, and then the other one is a parabola over here, path 2. Okay, and then path 3, there are sort of segmented path. So it goes to a vertical path and then horizontal path, and then finally there's another path given by some parametric form later on. So let's try to see how we do this. In this particular case, it's easy to, as a one-dimensional integral, the usual case, because you are given a simple curve which is y, well, it's a straight line, y equals to half x. Okay, are you seeing my cursor again? I need to check, otherwise I need to make a mark. Are you seeing my cursor? The arrow? Somebody? Great. Okay, so in other words, here is the function, and then you can now also remember that in your expression of w, there is both dx and dy. So you need also to find out, okay, can we convert, say, one of the differential into the other differential? So in this way, you can, because you are given y in terms of function of x. Okay, so you get that. And then the next thing to do is just to substitute. Okay, so you have over here xy, so y is half x over here, and then your dx. So we are using dx as the element of integral. Okay, and then the other one is going to be y squared. So this is y squared over here, and then you have your dy. So dy will now replace by half dx. And then you start to simplify this here. So let me bring this up. Okay, simplify this expression, and it essentially gives you that integral, which is enough for you to do, and that gives you the answer 1. Okay. The next one is to take the parabola over here, okay, going from here to here, using the parabola, and the parabola is just a quadratic function here. And again, we can find out what differential of y in terms of x over here. And again, we do the same thing, substitute everything over here. So here is again your y, and here's your y squared, okay, and then this is your dy. So again, everything substituted in, then simplify the equation, and you have this integral to integrate, and that's easy enough. Again, just do the usual integration, and then you find the answer is 2/3. Okay, so this is a crucial point at the moment. We are using two different paths, and we get two different answers. Okay. So next one, we also need to demonstrate how to do, let's say, you can break up your path. Okay, your path may consist of several segments. Of several segments, say, so here is a path P, f dot dr, say, and then what can be done, since you can break it up into several segments, you can simply just integrate over segment 1, say, f dot dr, and then segment 2, f dot dr, and the same thing if you have more segments. Okay, so in our case over here, there are two segments. One is a vertical path. Okay, this is going from 0, 0 to 0, 1. If you look at the previous picture, let me go up just to refer back to the picture again. Okay, you have this vertical path, and then you have this horizontal path. Okay, so so here is the vertical path. So the vertical path, you have your x to be constant, to be equal to 0. Okay, in other words, when x is constant, your dx is 0. So the only term that's going to appear is your dy. So here your dx is 0. Okay, so then the integral becomes just an integral over y, and you can do that easily. You get minus 1/3, and remember that this is only half of the path given, so you need to do the other half, which is the horizontal one. So the horizontal one is given by y equals to 1. Okay, y equals to 1 here, and then your x vary from 0 to 2. Okay, so then again, because of y equals to 1 is a constant, dy equals 0, so the only term that you're going to get is coming from dx. Okay, so again, the integration is simple enough, and then you get the answer for that segment. And then to get the whole integral, okay, the integral f dot dr over that disjointed, well, I mean, it's continuous, but it's having these segments of path, you need to just add those up. Okay, so the answer for the first one is minus a third, and then the second segment is 2, and then basically you get the answer 5/3. Okay, so that is one of the possible path. The other path that was given was path 4, and path 4 is given in terms of parameter. Okay, so your x is given in terms of 2t cubed, and your y in terms of t squared. Okay, and for each of this term, remember we need to find dx and dy. So, and one can convert this into dt. Okay, so again, the final integral will be only with respect to this dt. Okay, and then that's easy, and again, easy enough for you to do. The other thing that one has to remember is to look at what is the limits of the integral, because you have changed it from no, you have these points, endpoints of the path. Okay, so we need to determine what t gives you that and what t gives you the other endpoint. Okay, and it so happens that you can check for yourself. The first point, or the initial point, is given by t equals 0, and the final point is given by t equals to 1. Okay, so that that determines the limits, and then you can do the integral again. So again, all these different paths give you different answers. Okay, so is it possible to have a line integral which is giving you the same answer? Well, that's the next example that we're going to look at. Excuse me. So here's an integral. Again, over here it's not specified what path to take, but you are given this particular integral, which is really going from minus 1, 0 here to 1, 0. Okay, so the path that is shown in this figure, there are two paths. One is the semicircle, okay, and the other one is the disjointed, well, it's not this, it's segmented path. Okay, so the path 2. For the circle, instead of using your x and y, we can convert it to your polar coordinates, because it's easier to parameterize your circle by polar coordinates instead of x and y. And of course, you can use this the same coordinate transformation over here. Okay, x equals to cos theta, y equals sine theta, and of course you can get your dx and dy from there. Okay, so once you substitute those coordinate transformations into the integrand is given by that. Over here you can see your denominator gives you 1 because it's cos squared plus sine squared. Okay, that gives you 1 there. And if you substitute your x dy, y and minus y dx, you also get cos squared theta plus sine squared theta d theta. So the final integral Okay, the final integral over here, your I is just integral over theta. Again, one needs to remember how to put the limits. Okay, the limits previously was minus 1 0 to 1 0. Well, over here you have to remember how does your theta what you call varies. Your theta varies from your x-axis. Okay, so theta is going that way, but now you are required to move in the other way. Okay, so in other words, what happens over there is that you get this sort of opposite way of, no, instead of going from theta equals 0 to pi over here, it comes from pi to 0. Okay, so and these are easy to integrate now in terms of theta. Okay, remember your r equals to 1 in this particular case, your radius of your semicircle, and you can integrate that and it gives you minus pi. Now let's try to do the other path, okay, which is going from the straight line from minus 1 0 to 0 1, and then from 0 1 to 1 0. Okay, so let's do it step by step. It's on the other page. So from minus 1 0 to 0 1, one has to remember what is that particular line. That particular line is given by y equals to x plus 1. So once you write this equation down, then you can actually convert your dy into dx. Okay, and then substitute everything in. So here's your y, and then here was your dy previously. Okay, so this is dy and this is your y. Okay, and then you simplify this, and then you get this slightly integration to look at. Okay, because you have this square terms in the denominator, one could actually do look up the table of integrals, but if you don't have access to table of integrals, you can always do the following. Go back to the basics. So what do? You take 2x plus 1 to be equals to tangent theta. Whenever you see this 1 plus something square, it's always good to put it as tangent theta there. Okay, because then you can see that 1 plus 2x plus 1 square becomes 1 plus tangent squared theta, and this is secant squared theta. Okay, so once you do that, what will be your dx? Well, dx will be related to d theta in this following. So you substitute all this, and then you should be getting your I think if you do this, let me go to this side. If you do this, let me just check my notes. What will you get? You would get again a similar thing that you have seen in the case of the semicircle. You get integral of d theta. Well, why is it d theta only? Well, you have remember the denominator is essentially secant squared theta. Your dx over here is half secant squared theta. Okay, so the secant squared theta top and bottom will cancel out to give you d theta. I think there's a factors. Let me just check. Oh, the factor of 2 and the factor of half over here from that dx there cancels off, so that you only have d theta there, and now we need to determine what is the limits in this particular case. So again, what do? You look at the defining equation there. So when x equals to what was it? And x equals to minus 1, right? X equals to minus 1, your tangent theta becomes minus 2 plus 1, which is minus 1. And that tells us theta is going to be going from minus pi over 4. So that will give you minus pi over 4. And then again, the other limit would be 1, 0. Your x equals to 1. So x equals to 1 gives you sorry, x equals 0. Remember the top point is 0, 1. Sorry about that. Okay, top point is 0, 1. So x equals 0 there. Then your tangent theta will be equals to 1. So theta will be pi over 4. So integration of that would now gives you I think I forgot the minus sign there. There's a minus sign there. Okay, so it should be a minus sign. That will give you minus pi over 2. Okay, so the next one will be the other part, which is this one, and that is given by this equation with a negative slope, y equals to 1 minus x, and dy equals to minus dx. Again, the same thing, same trick. So you get this again, a same kind of the form in the denominator. You can do the same trick, and again you get another integral in terms of your theta if you want, and that gives you minus pi over 2. Okay, remember these are the first part, the first segment, and then this second segment, and then you add them up. So your I is going to be equals to minus pi over 2 plus minus pi over 2, which is minus pi. Okay, and you can see that this is just the same answer as the one we had before using the semicircle. Okay, semicircle we get minus pi, and then followed by this, which is the segmented path. Again, you get minus pi. So now the question arises: when does the line integral give you different answers for different path? When is the line integral gives you the same answer for different path? So remember, our problem lies in the integration of your f here. So really whether this is going to be dependent on the path depends on the nature of f. And in physics, you probably have understood this, because if you take the work done for the case of, say, some friction force, okay, and friction force, it depends on how far, how much displacement is actually been done. Okay, so the more displacement, the more work is done by the friction. Okay, so in that particular case, then we will see that okay, this will be dependent on path. But there are forces in physics that you have already known that it only depends on the endpoints. And these are what we call the conservative forces. Okay, so friction force essentially is non-conservative. forces that only depend on endpoint dependence here, then this is what we call conservative force. Now, how can you actually see this? Well, usually what happens when you do conservative force, go to the next page, you are able to write down your force in terms of a potential, del W. Okay. So in other words, your force vector are given in terms of this derivative of a particular function W here. Okay. So one can write in this particular manner if you want. Okay. But let me just mention this. The usual thing that you see in physics textbooks, you probably see in this particular form. Instead of just gradient of W, you have minus gradient of phi. Both are actually equivalent in a way, okay? But this has some physical meaning. Later on, we shall see one example. Okay. So what happens in this particular case is that once you put it in this particular form, let me go down. Then your f dot dr becomes del w dot dr over here, and essentially this will convert into that, which is now, no, you have done differentials before. These are just the differential of the function w. So when you do this integral from one endpoint A to another endpoint B, then it's just the function w evaluated at the endpoints B and A there. So the difference between the two. So that in that particular case, it doesn't matter if your f is written in terms of del w. It doesn't matter which path you take. Okay, so it only depends on the endpoints. There is one thing that one needs to check. How should I say this? One needs to check this. The idea of having a single W sometimes may break down. Okay, so one needs to check this idea of this mixed derivative over here. Okay, should tells us, okay, if you swap your y and x around, okay, then it gives you the same number, same quantity. So in this case, one of the things that you need to check is derivative of y of f of x, sorry, f x component of x, f, sorry, and then this must be equals to the x derivative of y component of f. Okay, so this may break down, and this kind of relation is sometimes called, I think it's mentioned over here somewhere. Okay, I can't remember. Maybe it's next page. It's sometimes called reciprocity relation. Let me just check on the next page. Yeah, this is for a particular case. Okay. So you need to check that is always true. Okay. Again, this. Okay. So let's Oops, what do I do here? Okay, here's an example. Okay, before that. So, how can you tell? Oops, how can you tell? Why is it not working? Sorry. Maybe I have to click on the page first. Yeah. How to essentially check whether your force is conservative or not? Well, one of the things that we know is this vector identity. If you take curl of f, what does that correspond to in this particular case is this is curl of gradient of w. When you find the gradient vector product with the gradient, this is equals to 0. Similarly, if you do it in the other form, the more physics friendly form, okay, this is 0. Okay, so that is the thing that you can actually check before you begin the line integral. Okay, you can check whether the force is actually conservative or not. So once you know it's conservative, then a good thing to do is to find the most convenient path, because it's now path independent. Then no, why do you need to do difficult integrals when you can take the most convenient path that gives you an easy integral? Okay, so here are some. I hope I'm not disconnected. I'm not getting messages here. Okay, here are some examples over here. So here you have this particular force given in this form, and then you can actually check this. There is well, later on we talk about this potential thing, but you can check your curl of f is going to be equal to 0. So in other words, one can write this in terms of potential, and how do you get a potential we can see later on. So there you find that, okay, you can simply integrate with one particular path, and then you can get the answer. So how to find the what you call well, okay, in this particular case, your W is already the answer that you need. Let me just see how this actually works. Here you are getting the answer instead. Yeah, okay. So over here, what one does is to integrate to, so usually what happens over here, okay, usually what happens over here, when you integrate this, these are specified points A and B, you get a value, okay, if A and B are specified. But one could do, in order to find out what the expression of this potential, for example, so you want to be able to see what potential correspond to this particular force, one could actually do this kind of trick. So one sort of segmentize your path into few parts, say going from a particular path from 0, 0, 0 to x 0, 0. So in other words, over here, your y and z are constant. Okay, so in other words, this is sort of going through, let me draw the diagram if I can. So these are just going through no, this direction. Okay, and then no, maybe the path is somewhere here. Okay, so you sort of, well, okay, maybe I'm not, maybe I should do this. So let's say you have the 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 points or the endpoints are here and here. So you can go from x equals to 0 to that x value here, okay, in that manner, okay, and then go to the y value, okay, keep x constant there, and then goes from, sorry, this is z, okay, come it miss a part. There should be an intermediate part where it goes from x00 to xy0. Okay. So in that particular case, you see your x doesn't change, so dx will be 0. Your y changes, so there will be dy, and your z is maintained at z equals 0, so dz equals 0. Okay. So one segments the path into these three parts where only one variable is varying for each segment, and then you can do the integration for the three segmented path, okay, and finally get the answer for your W. Okay. So over here, essentially, what are the endpoints? The endpoints are given from 0, 0, 0 to x, y, z. Okay. So when you do this, then you get your W as a function of x, y, z. Otherwise, if x, y, z are numerical values, then you get a numerical answer for your W. Okay. All right. Okay. Now let's go to an example for which you've seen this in electromagnetism. Have you done electromagnetism? Somebody? Not yet. Great. That's the way it should be, because you need to do vector calculus first to be able to do electromagnetism. Okay. So here is an example from electromagnetism. Okay, where one looks at electric field, okay, and what one does is to look at how it influences a particular charge on the by the electric field. Okay, so the electric field are usually given. So in this particular case, this is an electric field due to a point charge. This is about positive, I guess. So then your electric field will sort of pointing on the radially outwards. So this is Q here. So your electric field is given by this vector Q over R squared. Okay. So why is this R squared over here? Because as you move further away from the charge, the magnitude of the force or the magnitude of the electric field sort of decays. So it decays quadratically according to this what we call formula. Okay, and the direction of the electric field is radial. So there you already know that, okay, it's good to use polar coordinates in this particular case. So here you have your unit vector in the radial direction. But you can always convert this, you know that your ER is just a unit vector in R direction. Okay. And you can always do this by writing R divided by your magnitude. R without the underline is your magnitude. So that is what actually happens over here. So you're replacing your unit vector by R over vector R over R, and then you are now giving it in terms of the position vector, okay, which is sometimes more convenient to look at. Okay, so now let's see what this takes us. What is the potential? Okay, the potential again. This depends on convention really. The potential is, so here's a point charge, okay, the source. In order to see what the potential, one sort of, okay, this point charge is now having this electric field, okay, remember that. So how does one sort of detect the electric field is to bring a test charge. You put a test charge inside the electric field, then it will start to move according to whatever charges there is, and then whatever directions that the electric field actually points. Okay, so in this particular case, one normally has this convention to take the charge from negative infinity, sorry, from infinity to the point R, where the point R is simply x, y, z. Okay, remember how to, in the earlier case just now, if you want to find the potential, if you want to find the potential, you do this kind of thing. You take a path from the origin to x, y, z, okay, but in this particular case, okay, this 0 0 is just a convention. Well, it's just a choice, okay. So our choice now is to take the test charge going from minus infinity. I'm keeping saying, okay, in the usual way we think of x, y, z, that's why I'm saying minus infinity there, but in this particular case you're taking collectively thinking in terms of r, so it doesn't matter what is the direction there. So you just either go from infinite distance away from the source to some point x, y, z, okay, to the point R. So that is the convention that we do over here. Why do we take it from infinity here or minus infinity in terms of the Cartesian coordinates? It's because you expect the answer to be 0 over there. Okay, the value of your field is going to be 0 over there because it's decaying. So in other words, at infinity, the test charge would not actually feel the electric field. Okay, so that's why it's a convention to have this minus sign over here, because you're putting your integral is going from infinity to some point R. So that's why you have that minus sign. Okay, so then, okay, one integrates this. So your integral here was what E was given earlier. E was given Q over R cubed R. Okay. E equals to Q over R cube, which is your distance here, and then the vector R. So you have that now. So R, your vector R over here will dot your with dr, and then you need to do this particular integral. Okay. Well, R dot dr is what? Well, let's do this. Essentially, this is it's already over here. If you take d of r dot r, what do you get? You get dr dot r plus r dot dr. Okay, but this had because of your dot product commutative, or you can change order. Then this gives you 2r dot dr. Okay, but r dot r is essentially the r squared. So dr dot r equals to dr squared, which is now given in terms of 2r dr. Okay, so in other words, now I can write, because dr dot r is 2r dot dr, so I can write r dot dr in terms of vector, in terms of this sort of distance rather than the vector. Okay, so finally this becomes r dr over r cube. Okay, and that simplifies a lot, because otherwise you really have to think in terms of, okay, what are the angular parts of this integral, and then over here you sort of remove that totally by observing this relationship between the vector scalar product here with the distance over here. Okay, so then your r over r cubed gives you 1 over r squared, and then you integrate that, and I think here, because of the minus sign, we have already swapped. Okay, previous, it should be what? It should be q r infinity r dr over r cubed with a minus sign. Okay, but because of the minus sign, we can swap now your infinity with r over here, so that you get that. Okay, so the minus sign has been included there. So finally, what gives you the answer? It gives you this particular integral potential. Okay, I think that sort of I'm running out of time here. I will put up all these things probably from this point onwards. Okay, I will try to do this in a recorded lecture. So, and please be patient, because I have to do this step by step. So I will try to upload it, and when I upload this recorded lectures, I will inform you through the WhatsApp group. Okay. So I think that's all from me today. I apologize that we don't have proper lectures for this course. You have to go through some recorded lectures. Okay, so I think that's it. So let me take the attendance. Hopefully it doesn't cause me problem today. Well, I'm still having the same problem as yesterday. So what do I do? Trying to avoid see if I can save this in a different way. Save as. Okay, maybe maybe I do this. Let me see. Let me check first. Please bear with me a little bit. Teaching 604. Attendance. So let me put the date today. What's the date today? 26. Okay, let me try to check this. It's not happening. Let me go here. I'm sure you want to see that, but no. So where does it save? Show in folder. Oh, I still downloading. Sorry. Now, if you have other classes, you can leave if you want to, but if you don't, please don't leave yet. I just want to check the attendance list is there. It's there. Let's see if it records your attendance or not. Ah, okay, great. Okay, so we are done for today. So all the best for your coming exams. Uh, and I will keep you updated with the recorded lectures later on. I believe you have all done the selection of the papers for SCL. So we'll try to fix the date as a message in the WhatsApp. Okay. Okay. Thank you, everyone. Bye.
Thank you, Doctor. Doctor, can I meet you for a while?
Okay. You want to do this here or separately?
I think just here.
Okay.
Is it okay
So
for you?
yeah. Okay. So the rest can leave if you want to leave. Okay. Okay.
Doctor, regarding about our SCL, do you have example or any format that we have to follow? Because it's like our first time to do a review from a research paper.
Okay. With respect to that, no, you are free to be creative. Okay. Uh, the point is, if you remember in the instructions, you need to uh,
The characteristic that we have to
yeah,
follow there.
yeah. So you only need to do that. So it doesn't have to be so extensive. So because this is not meant to be like a project kind of thing. Okay, you need to understand what's inside the paper, and if you have not seen those concepts, then you tell what it is, that kind of thing. Okay,
Like just
like a summary kind of thing.
yeah, okay, okay. And for final, do you have the topic that you cover?
Okay, final. According to the university, the final will be comprehensive, all the way from chapter one until the differential equation.
Thank you.
All right. Okay. Bye, everyone.
Thank you.
Thank you, Doctor.